Have you ever thought that we can use machine learning algorithms to predict the properties of materials? To do this, you need three things: data, descriptors, and algorithms. There should be a big amount of sufficient data, which you can get from one of the online databases, for example, Materials Project. You can easily get access to all the data you need using the Python library called PyMaGen, which is based on MongoDB. Then you should choose the right descriptors and make a data frame with which you will be training your model. And finally, it's really important to choose the right machine learning algorithm. So as an example, let's look at one of the projects that I made. There I predict the band gaps of perovskites using machine learning. So here's my notebook with code. In the first lines, I import all the libraries I need. So here we can see PyMaGen. I import Ceph parser from it. PyMaGen MP raster, we also need it here. And here is my API key for the materials project. So first we need to create the MP raster with my key, with my API key for materials projects. Then in this line we parse all the, we request, the right word. We request the materials, which formula is this one. These are perovskites. So yeah, this is done by PyMaGen. By the way, it is based on MongoDB. So here I make a query with this formula, perovskite, as I said before, and we want to import properties, Ceph file, and the band gap. So the band gap is our target property. This is the one that we're gonna predict later. And the Ceph file is a text file that contains like all the information about our material. So here I have one. So it has a lot of text with information about materials. So yeah, these are like positions of different elements. Also there are angles between the bonds, and all other things can be received from this file. So let's get back to the notebook. So we get all our results, all our properties, all our information, and here we create the arrays for our descriptors. So here I included mean atomic numbers, max atomic numbers, mean atomic numbers, and STD atomic numbers. This is done because some of the perovskites have different phases, and they have different phases, so we want to do it like this. Then we have A parameters, B parameters, C parameters. These are positions in the space of the atoms. And alpha, beta, and gamma parameters, these are the angles between the bonds. And also we have distance matters, so this is like distance between different atoms. And of course we have the band gaps array because we're going to predict it. Here we import NumPy. And in this block, we're just filling our descriptors. So we get our Ceph file. So this is an array with all the Ceph files of all perovskite that we got. Here we import one Ceph file. We also look at its band gap. And then we fill our descriptors. I took band gap bigger than 1 because materials with the band gap equal 0. These are metals. And yeah, my model, when I tried to do it with metals and with metals and semiconductors, it worked really bad. It couldn't distinct metals from semiconductors. So here we take perovskites; those are only like only semiconductors. Yeah, and here we fill our descriptors. Then we import matplotlib.pyplot as plt. Yeah, we just set our parameters to a little bit look at our data. Yeah, and this graph shows how many elements in our array we have with different band gaps. So we can see that we have lots of materials. Those are band gap around 3, and we have really few materials. Those have a band gap near to 7. So then this is one more graph that analyzes our data. And then here, to train our model, we first need to create the data frame using pandas. Yeah, so here we create the data frame with all of our descriptors that we got earlier. And also we standard scale our data. This is how our data set looks like. So yeah, it has all of the descriptors that we generated before. This is just our data frame. So then we should train our model. We import from sklearn, we import train test split, and we split our data to the train data and to the test data. Usually train data is 80% of all the data we have, and the test data is 20%. So yeah, that's what we have here. Then we import mean squared error and R2 score, just to measure the performance of our model. And also we import the algorithms, like from XGBoost we import XGB regressor, and from sklearn.ensemble we import random forest regressor. So these are like both regressors. They do pretty same things, but they're just different. And yeah, here I tried 2 different regressors to train my model. And in this block we just train the model with random forest regressor, just some basic stuff. Yeah, and I make a graph with the performance of my model. So in the x-axis we have band gaps. Those are like calculated with DFT. Those were computed with DFT. So it's actually, yeah, our target band gap that we got. And in the y-axis we have the band gaps that we predicted, that our model predicted. And in the perfect world, all the data points should fit this line. So this linear line here. But here we can see the data is scattered, like in the beginning the data is scattered a little bit, but here our model did pretty good. And here it didn't do really well. Maybe it's because of the lack of data with 7 electron volts band gap. Yeah, it mean squared error equals 0.26%, which is pretty good. I find it pretty good. Yeah, and here we do like the same thing, but this is just another regressor. This one did a little bit worse. The mean squared error is bigger, but in general it did
pretty well. So it was all. You can find this code on GitHub in my TKS Live. You can find this code on GitHub if you want to download it. And yeah, that was basically pretty much it. Thanks for watching.